Hello and welcome back to Algebra 1 with Miss Betsy. Today we're going to begin Chapter 4, which is all about solving equations. We're going to be putting together the skills that you've been learning thus far, and you're going to see that it's really pretty straightforward to find, to figure out what x actually is in an equation. Now, if you are using the same text I am, this is what your book looks like. It is Algebra 1 for Christian Schools. It's the second edition, and it's published by Bob Jones University Press. You can learn, however, how to solve algebraic equations regardless of what text you're using. So we're going to be in section 4.1, using properties of equality. But first let's pray, and then I've got a lame joke for you, and we'll get started with our lecture. Father, thank you that you love us. Thank you that you are always there with us. I ask, Father, that you would help us today as we study this new section about solving equations, that you would help me to communicate clearly, and that you would help my students to grasp the concepts and to be able to apply them effectively. Thank you for your presence with us, and I pray in the name of Jesus. Amen. Okay, why do hummingbirds hum? That's our joke question for today. Why do hummingbirds hum? Well, they hum because they don't know the words to the songs. So in our last lecture from section 3.8, we were talking about properties of equality, and we learned that if you thought of an equation as being a seesaw or a balance scale, that your equation remains in balance if you add the same quantity to both sides of the equation, if you subtract the same quantity, multiply or divide, as long as what you do to one side of the equation you do to the other side of the equation. And we're going to use those properties of equality to solve equations. So I have 4 examples here, just of some algebraic equations. We have x plus 10 is equal to 142. We have x minus 17 is equal to a negative 35. We have 3x is 9. And then we also have x over 5 is equal to 21. Now, what we're going to do is be learning how to figure out what value for x makes each one of these equations true. And we're not going to just look at it and say, okay, what plus 10 is 142? I know x is 132. I know this right over here has to be a negative 18. I know this x here is a 3, and I know this x here is 105. It's not enough to simply be able to look at the equation and say, oh, I know what the answer is. Because what we're learning is a methodology to solve equations, because very rapidly we're going to get to where you cannot look at an equation most of the time and figure out what your solution is. So when we try, and you notice I just said solution, when you come up with a value for the variable, that is what we call the solution. The solution here would be x is 132. Solution here is x is negative 18. Solution, x is 3. Solution, x is 105. And in order to solve an equation, what we have to do is undo an operation. And you'll know, and this is the first time that we've talked about solving equations. And that's because to solve an equation, it's not simply enough to have an expression that says x plus 5. This is an algebraic expression because it has a variable in it. But it's not an equation that we can solve, because what value is this? Well, maybe it's 17 if x is 12. Maybe it's a negative 3 if x is a negative 8. Maybe it's 5 if x is 0. So you cannot come up with one single solution to this algebraic expression x plus 5 unless it is a complete math sentence, which is what we call an equation. And we do that by putting in our mathematical verb. X plus 5 is 6. Our equal sign is what ties everything together and lets us say, okay, since we know we have to end up with 6, I can find the one value for x that makes this true, and of course it's 1. And that's what we're going to be learning how to do. And it is mandatory that you show your steps and that you do your work in the method that I'm going to show you here and the method that your book shows you, because you're learning the process. You're not just looking at expressions saying, Miss Betsy, I know what the answer is. I'm glad you know what the answer is, because then you can check your work and make sure that you've solved it correctly. I said earlier that to solve an equation we have to undo an operation, and this is what they call inverse operations. And we've talked about these. Many of you have had me in another class. Inverse operation, it's the operation that will undo a given operation. And of course you just want to stumble all over that operation word, the operation that will, because you use it so frequently. And we're talking about inverse operations. They're things that undo one another. Back to my jacket illustration. You put on a jacket with a zipper, you zip it up, that's an operation. You unzip it, that undoes your original operation. You're back to what you started with. So zipping a jacket up and unzipping a jacket could be considered to be inverse operations. And let's look just real quickly at their examples here. We've been talking about this, so this should not be new material to you. If we have 7, we start with 7, and we add 8 to it, that's going to be 15. But instead of adding 8, instead of saying that that's equal to 15, we're just going to say 7 plus 8 is 15, minus 8 is equal to 7. What we started with, 7, and what we ended up with are the identical values. What if we had 7 times 5? Well, 7 times 5 is 35, but what if we go ahead and divide by 5 again? 35 divided by 5 is 7. What if we have 18 and we subtract 6, gives us 12, but we add 6 back again, we have 18, don't we? And you see what I'm pointing out to you here? These are what we call inverse operations. We've added 8 and then we subtracted. We multiplied by 5 and then we divided. We subtracted and then we added. So multiplication and division are inverse operations. They undo one another. And addition and subtraction are inverse operations as well. And we are going to be using inverse operations to solve equations. So let's look here at page 130. It says, to solve an equation like x plus 10 is equal to 145. How are we going to solve this? We already know 142. We already know that the solution here is 132. But what do? Well, first, we want to look at the variable. What has been done to it, or what's happened? X, if we started with x, what happened? Well, we added 10, okay? What we want to do is look at the variable, figure out what's happened, and apply the inverse operation. So if we added 10, what's the inverse operation going to be for this particular problem? We've added 10. The inverse is to subtract. So we started with x, we added 10. Subtraction is the inverse of addition, so we're going to subtract 10 from both sides of the equation, and we have 142 minus 10. We have to look at the variable, see what's happened. Apply the inverse. Both sides of the equation. And that comes from our properties of equality that says an equation stays in balance as long as you add to both sides, subtract from both sides, multiply both sides by a number, or divide both sides by a number. Now we have x plus 10 minus 10. And your book, I don't believe, shows this. Actually, they're going to, and I'm going to go ahead and illustrate it here. What is plus 10 minus 10? It's a 0. So you have x plus 0 is equal to 132. And our additive identity property says that x plus 0 is just the same as x. And right here is how we have solved x plus 10 equal to 142. We've found our solution of x is 132 by applying the inverse operation of addition, which is subtraction, and by subtracting 10 from both sides of the equation. This is what we're going to be doing forever now, and your work should look like this. Your work should be very, very similar. Now you're going to say, Miss Betsy, do I have to use different colors here to highlight the inverse operation? No, you don't. But if you're struggling with trying to figure out what you're doing, use different colors like I do, because then it just jumps out at you that you have applied the inverse to both sides of the equation. Okay, let's go ahead and do another example. Okay, example 2 says solve x minus 17 is equal to 35. Negative 35. What's the first thing that we want to do here? We want to look at that variable x. If we started with x, what did we do next? We subtracted 17. So what is the inverse of subtraction? Yeah, it's addition. So we're going to add that 17 right back, because inverse operations undo one another. If we add a 17 to the left-hand side of the equation, then we are going to also add a 17 to the right hand of the equation as well. Negative 17 plus 17, and we have x plus 0 is equal to a negative 18. How did I do that? When you're dealing with oppositely signed numbers, subtract the smaller absolute value from the larger. 35 minus 17 is 18. And we go with the sign of the number that has the largest absolute value. So we have x plus 0 is negative 18, or x is equal to 18, and that is our solution. It's been simplified, and we want to check. So how do we check? Well, you check by taking the value that you arrived at, substituting that back in to your original equation. We have negative 18 minus 17. Is that equal to negative 35? Yes, negative 35 is in fact equal to negative 35. So we have solved our problem correctly, and we verified that by showing our check. All right? Now, this check is something that you can do mentally, and not only can you do it mentally, it really, looking for my lid, it really makes very little sense for you to not check it mentally, because that will help you to find your errors. However, the only time that you're going to be required to show this check is if your problem says solve and check. If your instructions tell you check, that means half of your problem is involved in showing me the check. And if you don't show me a literal check there, then you miss half the points on your problems. And that would be really sad. So let's go ahead and see what our next example is. This is example 3. Solve 3x is equal to 9. And we already said for this that we knew that x was going to be equal to 3 because 3 times 3 is 9. But what did our instructions say that I just erased? It said look at the variable and see what happened to it. Well, if you started with an x, what did we do? We multiplied by 3. So what is the inverse of multiplication? Do you remember? Division is the inverse of multiplication. And I'm going to say use the fraction bar, because this is going to make your work so much easier rather than that little raised dot thing that you have to work with. Use your fraction bar. And why are we going to use that fraction bar? It's because we can cancel common factors. 3 divided by 3, we have x. 3 goes into 9 3 times. X has a value of 3, which is what we knew was true, but we used the property of applying an inverse operation. We started with the variable, saw that it was multiplied, remembered that multiplication and division are inverse operations, so we divided both sides by 3 to end up with our true solution. Now, if we had to check this, we would substitute in, instead of that x, we would substitute in a 3, and we would see if that made our equation true. 3 times 3, is that equal to 9? Well, yes, of course. 9 is equal to 9. And that's the way that we have verified or validated our solution. And if they ask you to check, this is what they mean for you to do. So let's go ahead and look at example 4. And this is the fourth one that we had over here, where we said that x was going to be equal to 105. And some of you probably saw how I did that, and some of you thought, what in the world did you do? Well, let's see if I'm right. X over 5 is equal to 21. What do we do to solve this equation? The first thing is look at the variable and we see what's happened to it. If we say x over 3, x divided by 3, except it's a 5, not a 3. X divided by 5, the inverse of division is multiplication. So we are going to divide both sides of that equation by 5. Can cancel common factors. And we have x is equal to 105. Exactly like I said. To check it, you would substitute in 105 for x, and actually do that division and see if you ended up with 21. So 105 divided by 5, of course, is going to be equal to 21. 2 times 5 is 10. Bring the 5 down. 1 times 5 is 5, and there is no remainder. Over here is the check. You should always, always, always be doing a mental check. Make sure that your answer is reasonable, and if you think, I'm not sure. Like if you said 15 here. that ought to jump out at you as there being a problem somewhere. Okay? Now we have another type of equation that we can solve, but first your book reviews for you on page 135 what do you do to solve an equation. I'm not going to write them again. We had those over in the board to the right side to begin with, and you have this material in your textbook on page 132. What do you do? Very first thing, it says determine the operation performed on the variable in the equation. What happened here to x? They divided it by a quantity. Secondly, we're going to perform the inverse operation on both sides of the equation. It has to be done on both sides so that equation remains in balance. If we have divided, the inverse operation is multiplication. If we've multiplied, the inverse is division. Just like addition and subtraction are inverse operations to one another. Then you simplify both sides of the equation. I want you to notice that what we're doing here is we are isolating the variable. What that means is that our goal in working through these steps to solve an equation is to have the variable and the variable alone on one side of the equation. Doesn't matter if it's on the left-hand side or if it's on the right-hand side. The goal here is to isolate the variable, have the variable all by itself. And that's what happens when we have simplified this equation. We have x is equal to something. And then the final step that you should do would be to check your solution and make sure you have the right answer. And here they don't mean get out the teacher's manual and check it. They mean actually go ahead and verify for yourself that you have arrived at the correct answer. Now there's one more way that you can deal with equations, and these are what they call literal equations. And it really doesn't make sense unless you sort of slur the literal into literal. Solve x plus m equals n for x. Solve x plus m equals n. Solve for x. What we are solving for is what we want to isolate. That's the variable we want to isolate. So we want to have x all by itself, which means that we need to look at x in our original equation and see what's happened to it. What happened to it? They added m. So we're going to apply the inverse of addition, which is a subtraction. So we are going to subtract m from both sides of the equation. And we have n minus m. So now we have x plus m minus m, x plus 0 is equal to n minus m. X is equal to n minus m. That's supposed to be an m, and you say, there are way too many letters in there. I understand, it looks weird when you have an answer that just has letters. But we followed our rules, and it said, look at the variable, see what's happened to it. We added m. Apply the inverse, which would be to subtract m from both sides of the equation, and then simplify. So let's go ahead and check it and see if we're correct. What do we do when we check? We substitute in the value for the variable. So we're going to have n minus m plus m. Is that equal to n? Well, I could actually rewrite this with the parentheses around the negative m plus m. That's the associative property that says you can rearrange the grouping. but I'm not going to. Minus m plus m, so you have n plus 0 is equal to n is equal to n. These are what they call literal equations. And literal equations are always going to have a variable in the answer. So let me put that here. We'll always have at least one variable in the solution. So, have fun playing around with these. I think that once you get the hang of it, this should be a pretty enjoyable section for you, but as always, if you have difficulty, send me a text, ask me a question on Friday, and I'll see you next time.